Welcome to a lesson with Dr. Powell. Let's talk about the basic idea of why limits commute with a Hom functor. For instance, let's consider having a limit, having a commutative diagram. Let's just draw two things in that commutative diagram. And what's a limit of a commutative diagram? It's kind of like something that we can extend the commutative diagram with, where we have maps or morphisms that go from L to each object in the commutative diagram, such that it's extended, and it's just kind of like a mega bigger commutative diagram, but it's done in a unique way, such that if we do it with anything else, like if we did the same process with something else, then there's a unique morphism from S to L, such that it extends this one to even a bigger mega commutative diagram. So using that basic idea, let's talk about this. Let's go back to the case here where we just have where we have a limit of a diagram, and let's apply a Hom functor to it, a covariant Hom functor, Hom A to L, say right here, so that we get again a diagram. Now, when we do this, we don't have a guarantee that the limit necessarily is preserved. I mean, we have this commutative diagram, but we don't know that this is the unique guy kind of at the forefront of all the other ones that do the same thing anymore, because we have different objects and different maps. But let's kind of think about what would happen. Let's just take something here in the category of sets, because that's where the output of the Hom functor is, say, at least in this particular situation. All right, so let's take S, and let's suppose that it maps to all the different set outputs of the Hom that we have going on. We have this commutative diagram in sets here, and suppose that S goes to each element of that commutative diagram to make a bigger one. All right, now the goal is to show that there's actually a unique set map that goes from S to this Hom functor. What that would do is that would guarantee that the Hom is actually the limit of this bigger diagram, which meant taking a limit on the inside was the same thing as taking a limit on the outside. So really, that's all we need to show is, do we have a unique map going this way? So let's back up and think, okay, what if we had something like a function here, or an element of S, that is. So if we take an element of S, okay, I'm going to just call it maybe like X, okay. Now, what is X going to go to? Well, we're supposing that we already have these maps here from S into this commutative diagram. So X has an image here, over here. So what is the image? Let's suppose the image is F, say. All right, now F will naturally map over here. How so? Well, think about how the Hom functor works. It's a functor, so it maps morphisms as well. So suppose in the original commutative diagram, we have a map from Pi to Pj. Suppose it's like delta ij. Now we take F, which is a morphism from A to Pi. So where is it sent in this map of Homs? It's actually sent to just this composition, delta ij of F. Okay, so what we get is, if X is sent to F here, X would have to be sent, because of the commutative diagram situation, X would have to be sent to this guy over here. So X is sent here, X is sent there. So let's think about that for a minute. I mean, that's kind of interesting here. Actually, we kind of see a beginning of something like f is going to pi, but then so f is a map from a to yeah, from a to pi. But if we have a map over here, let's suppose we have a map that from a to pj, we know that g is equal to this composition. And similarly, for any kind of situation that we have here, um, we have this going on. So what we have created actually is we've created an extension of the commutative diagram of P to A. And simply that was, and all we've done is said, well, let's see, X must go to F and X must go to G. Basically, by making all of these things, we've like naming all these functions here, we've actually named the destination of where X goes to all these pieces of the commutative diagram. So by assuming that A extends this commutative diagram is the same thing as saying that S extends this commutative diagram. It's equivalent. So, well, that's kind of handy because that actually means there's a unique map from A then to L to make everything work here. Okay, well, okay, so given an X here, we got this commutative diagram, which gave us a unique map to L. Well, that's like saying you have a X2 map from A to L, a unique map. Oh, this is a unique, it's a set map. That's all we needed. A unique set map from S to there. And so we get something very nice is we have this uniqueness going on here. This is a unique map from S to HOM from A to L, which means that this right here happens to be, this is the limit of that diagram. So we actually have shown that that's the limit of the diagram, and hence limit on the inside becomes limit on the outside. Thanks for watching.